Hello everyone and welcome back to NL 582 Modeling and Control of Electric Machines and Drives. And the last couple of times we started talking about three-phase induction motors. We said that it is a very important machine to understand because it is the workhorse of industry. You'll be seeing this kind of motors in almost every facility you can deal with, whether it's a power system facility or any industrial facility. Okay, it is the most commonly used kind of motors, so it is very important to understand its operation, model it, and understand how it works actually. Okay, so we started talking last time about the stator of this machine and how it creates its own field, and we just said that the stator of three-phase induction machine, just will abbreviate it like IM like this, holds or just has an iron core like any other member in a machine actually, with slots holding three-phase balanced winding. Okay, and we said what we mean by balanced winding. It is just you have three typical sets winding. They have exactly the same number of turns and the same dimensions, but they have 120 degrees phase shift between each winding and the next one around the circumference of the stator. Okay, those three-phase balanced winding fed from also a balanced three-phase voltage source. Okay, and also balanced three-phase voltage source, like we said before, it's just the three voltages have the same voltage magnitude and frequency, but they have 120 degrees phase shift between one voltage and the next one. Okay, that means they are balanced. This combination, that means three-phase voltages feeding three-phase winding, both of them are balanced, that will create a rotating magnetic field. Okay, we just derived this in very much details last time. Okay, so the rotating magnetic field, that means you have rotating magnetic poles. You have north and south poles rotating around the circumference of the stator at the synchronous speed, ns, which equals 120 f over p. F is the frequency and p is the number of poles. That's what we said or derived last time in last lecture in very much detail. Refer to it if you just don't remember how this happens. Okay, so we need this motor and any kind of a motor to produce torque. Okay, so how actually the torque production happens in this kind of machine, or actually in any kind of machines. Okay, so in any kind of machines, this torque production happens in two ways, like we said before. We have the saliency torque, which requires your rotor to be a salient pole, which is not the case in this motor. So the rotor of our motor is not salient pole, so we don't have this component of torque. In synchronous machines before, we said that the rotor of the machine can be salient pole, and like that, if you have a synchronous motor with a salient pole rotor, it will have a torque created by saliency. Okay, but here we do not have this, so the rotor of our machine does not have saliency. The rotor of the induction motor is cylindrical. Okay, cylindrical means non-salient, it's not salient pole, so you do not have this part of torque here. So we create torque in induction machine in just the other way, which is the excitation torque. Okay, so let's understand how the excitation torque happens. We talked about this before. So the excitation torque, that means you need, or it requires, two components of flux, of magnetic flux. Okay, one from stator and the other from rotor. Okay, the combination of them, like we said before, the combination of those two fluxes creates torque. Okay, there is a general equation to govern this is just saying you can find the torque actually that comes from this, applying that the torque of the motor can just be found by K, which is a constant, multiplied by the rotor flux, which is vector cross the stator flux. Okay, so this BR the rotor flux, rotor magnetic field, rotor magnetic flux, and BS is the stator flux. Okay, so you need those two components. You need rotor flux and stator flux in order to create torque. Okay, the motor torque, develop torque. Okay, so here's the whole thing. We need two component fluxes. So the first one, the stator flux, comes like we said last time. Okay, so the first component we already had it. The stator flux, this component, the stator flux, comes from the stator three-phase excitation. Okay, you are just applying three-phase voltage to your stator winding, and that means the voltage will just apply to the winding. A current will be moving through this winding and will create you with the rotating magnetic field we've been talking about since last time. Okay, so we already now understand how the first component of flux, which is the stator flux, comes from. But what about the rotor actually? Okay, so we now understand that we need another component of flux in the rotor. Yes, so let me remind you this. The rotor flux in both synchronous machine and DC machines, the two kind of machines we already dealt with since now, okay, the both rotor flux of them comes from DC excitation via brushes. Okay, so if you remember, we used an external source. So DC excitation, what I mean here by external source, there is a source that's connected directly via the brushes to the rotor to provide it with voltage, and this creates current, and the current moving through the winding creates you field. Okay, so just like the stator, so the stator has a source to push the current through it, so you have current moving in the stator winding, and this creates the stator flux. And also the rotor has a source that is connected to it via the brushes and slip rings in the synchronous machine, and via the brushes and commutator in DC machines. Both of them are just pushing electric current into the rotor winding, and this creates you the rotor flux. Okay, but having the brushes, those brushes actually something we do not like much. Why? The brushes, guys, requires, okay, frequent maintenance. Okay, why? Because wear and tear happens by friction and also electric sparks. Okay, so if you remember what I mean by a brush, actually we said that if you have the cylinder of the rotor just like that, and there is here around it, so that is the rotor, the shaft, right, and around it here you will have a slip ring. Okay, another just cylinder on it, so this is a slip ring. Okay, and this black guy here is the shaft. Okay, and both of those actually are rotating. The shaft is just, that's the rotate that's attached to the rotor, and the slip ring actually is just attached to the shaft, so both of them are rotating. And you use the brush just like that. The brush is just attached to it from the other side, so that's the carbon brush, and you have a spring here to keep it pushed like that all the time, to be touching the surface. This is the brush, okay, the carbon brush. But the carbon brush is fixed, it does not rotate anywhere and doesn't make, that's the whole point. Okay, so the slip ring and shaft are rotating while the carbon brush is fixed, and that's why you can connect your voltage source to this brush to push electricity through it to the slip ring, and from the slip ring that goes to the rotor winding. Okay, but imagine about that. You have a fixed part, which is the carbon brush, all the time has to be pushed to be in contact with a moving part, which is the slip ring, which is attached to the shaft. Okay, so all of that will have that those two parts will be just have a friction together all the time. This friction will happen, will just cause a wear and tear on these brushes, and also because there's a current moving from the brush, which is fixed, to the slip ring, which is moving, you will have a tiny gap between them, and this will create electric sparks all the time. And this spark will also wear and tear these brushes. Okay, so the brushes, whatever any system you have, guys, that have brushes, that will cause you headache all the time, because the brushes will be needing frequent maintenance. Will be needed also to just clean the surface of the slip ring, not to leave any particles over there, because this will increase the sparks that happens. And frequently you need to replace the brushes, because this wear and tear will just give you more and more electric sparks, and that is not something that's good. Okay, so the idea of pushing electric current to the rotor winding from external source all the time requires to have, or most of the times actually requires to have this set of brushes. Okay, and like we said, that means you need maintenance all the time. Let me give you a little bit of a secret. For all the engineering aspects, we need to reduce maintenance requirements as much as we can, because we like all the time to just put the system out there and forget about it. Okay, so any system that requires a lot of maintenance is just not something desirable in the engineering world. Okay, so we can pay more money sometimes, and sometimes we can even afford to have a machine that is the performance that is just poor compared to other machines, as long as this machine requires less maintenance. Okay, so sometimes we can sacrifice many things just to have a low maintenance machine, or what we call a maintenance free machine. Okay, so here comes actually the very, very important aspect about the induction motor. Okay, so not like DC and synchronous machine, while the current or the rotor current comes from external source. Okay, so the rotor flux here in both synchronous machines and DC machines come from external source, and that requires to have brushes all the time, and that comes with the cost of frequent maintenance. Okay, the rotor flux in induction machines comes by induction, and that's why it's called an induction machine. Okay, how this happens, I'll be talking this in much details just in a second. But before talk how the rotor flux comes, let us just first talk about the construction of the rotor. Yeah, so yeah, let me start here. I'll talk about here the rotor construction. Okay, how the rotor of this machine is built actually. So you have two types of rotors in this kind of machines. Let me grab you a more realistic photo here. Yeah, that's it. So in the induction motors, you have two types of rotor that can be used. Okay, the left hand side one, the slip ring motor, single rotor. Okay, we call it sometimes the wound rotor. What? Okay, the other thing, and the right hand side one, which is the most commonly used type of rotor with induction machine, it's called a squirrel cage rotor. Okay, or sometimes we call it just cage rotor. Yeah, so the first one, the slip ring, and the second one is the squirrel cage one. Yeah, so let's talk about each and every one of them and alone. Okay, so yeah, let me try to have it like that and talk about them. Yep. So for the slip ring, just like you're seeing it here, the slip ring or the wound rotor, okay, the rotor is exactly like stator. Okay, what I mean by that, it is have an iron core with slots and three-phase winding placed in these slots, just like the stator. So the rotor will be just like the stator, like you see in here. You have an iron core like this and just have slots inside this iron core, and you have these winding, three-phase winding, okay, just like the stator, placed in those winding, okay, placed in those slots actually, okay, and okay, those three-phase winding terminals of those three-phase winding are connected to slip rings and brushes, just like in the synchronous machine and the DC machine, but here you have three-phase winding, not like DC machines and synchronous machines. DC machines and synchronous machines, they have just one winding because they're fit from DC supply, so we just need one winding. But here we have three sets of windings separately, and that means you need here, like you're seeing here, those are three slip rings separated from each other, and you have three brushes like that. So those are the brushes and those are the slip rings, okay? Obviously that is your shaft, okay guys? But that means it have the same problem we said before. It has brushes and we don't like brushes. Yeah, okay. And that's why we can deal with the other one, which is the squirrel cage, okay? So the squirrel cage rotor, like you're seeing here, because let me just let you to understand this idea. The winding of the induction motor are shorted, okay guys? Okay, so yeah, before we just jump into that, so not to confuse, so now we're talking about the slip ring round rotor machine. It's just you have three-phase winding in the rotor just like the stator, and those terminals are connected to slip rings and brushes, okay? So you're asking now, why are those three slip rings and three brushes while you have three winding? That means you have 6 terminals, yeah? You have 3 coils, that means you have 6 terminals. But we need to save and don't have just the need for 6 different slip rings and 6 brushes. We will be called, it's just 3-phase winding, you know, so we connect them internally to be a Y or delta, and we just have 3 terminals out of them. So the winding, the 3-phase winding, are internally connected. So 3-phase winding, those 3-phase winding here, internally connected, okay, like Y or delta connection, like any connection for 3-phase winding, yeah. And you have just 3 lines connections from them that goes to 3 slip rings and 3 brushes, okay. So this slip ring rotor, round rotor kind of machine, let me keep doing like that, is used. So the wound rotor or the slip ring type is used only if we want to access the rotor winding for control or generation purposes. So the wound rotor type, we do not use it unless we want to access the rotor winding for the case of control. We'll be talking about this in much details later. So we can try to connect those rotor winding to any other system outside the machine, okay, or connect it to an external source if we want the machine to act like a generator, okay. But if you're talking about just a motor, we don't want it to be a generator. Sometimes we use also the rotor circuit, the rotor winding, add some resistance, external resistance to it to control the speed of the machine, and we'll be talking about this in much details later, okay? But if you don't need to access this, okay, so, or we just short circuit the three-phase winding. What? Like an electrical engineers, we hate short circuits, yep. But the way how this motor acts, how the torque is created here, it requires the rotor winding to be short-circuited, okay? So just bear with me, I will be just talking about this in a second. But for now, if you just have the motor to work as the test, so it's short-circuited to, to work as a motor, okay? So for the motor mode, you just need the rotor winding to be short-circuited, okay? So if you're gonna use, we're just going to use the slip ring rotor type, okay? So if you just don't want the machine to be controlled in speed via the rotor circuit, or you don't need the motor, this machine to work like a generator, you want just to act like a motor, you don't need anything but to short-circuit those three together, okay? So you just add from those three slip rings here and three brushes, so you just connect those three brushes together to act like a short circuit, okay? How the motor will act like that, we'll be talking about this in a minute. We'll just illustrate how actually this works, but for now keep that in mind, okay? So because like the typical working conditions of this machine, we want it to act like a motor, and we don't need to access the rotor circuit for control purposes, we just want to leave it work as it is, so we just need to short circuit those winding. And because we just need to short circuit those winding, here comes the other guy here, which is the squirrel cage rotor, okay? Because if you want those winding to be short circuited anyway, so you don't need all of this headache to have winding and connect them to slip rings and get the slip rings to brushes, and after this we just short circuit the brushes. It doesn't make sense. You can just short circuit them together at all, okay? But before jumping to this, to have this in mind, because you're now having so this guy still has brushes and slip rings, okay? That means it requires frequent maintenance, okay? So it still have the drawback we're talking about. You still have those brushes set and all that time, okay? So here comes the very brilliant idea. If you don't need to have anything connected to the rotor winding, you just need the rotor winding, and you will short circuit those carbon brushes, so it doesn't make sense to get all of this headache. We just switch to the other type, which is the squirrel cage rotor. Like I said here, or like you can see from this guy here, so the squirrel cage rotor is we place solid bars of copper or aluminum, and actually most of the time it's used like aluminum because it's more cheap, okay, and the rotor slots, and place two end rings of the same material, which is copper or aluminum, whatever it is, at their ends to short circuit them, and that's it. Like you see in here, you just need those, so those bars, aluminum bars here, are just like that, so those are your conductors of the rotor, and you just use those discs. So that's a disc and that's another disc. This is end ring, we call it like that, and this also is an end ring, and those are the bars conducting bars. Okay, guys? Like you're seeing here, those are short-circuited. So this end ring is conducting also. That is conducting end ring. It's the same material of the bars. Like you're seeing here, now you have winding in the slots, and those are just using those two ends from both ends, two end rings from the both ends of the bars to connect them all together, so they are all now short-circuited together like what you need. And now you don't need to have brushes, you don't have to use slip rings and all that headache. Okay, and this will give you what you need from this. Okay, so yeah, you have a problem here, is you cannot access the rotor winding for control or generation, and that means only stator side is used for control or generation. Okay, so if you want to do any kind of a control or to use the machine to act like a generator, you just play with the stator. You can just control the stator voltage, the stator current, the stator resistance, whatever you want to control with the stator, but the rotor will be just dead. You cannot access it. Okay, because you don't have terminals out of the machine. So the machine is just, yeah, you don't have the rotor terminals out. You cannot connect anything to them, and that's bad thing. That's actually a disadvantage. Yeah, that is actually a con. So this guy is a disadvantage. Okay, not like the wound rotor type where you can just access it, that you can access the rotor for all that type. You can access the rotor circuit because you have a terminals for it via the slip rings and brushes, and you can use it for control and generation. Okay, so in the wound rotor, the advantage of it is you can access the rotor winding. The disadvantage of it is you have slip rings and brushes, and those requires frequent maintenance. Okay, guys, so for this is a disadvantage for the wound rotor machine. Is just for the wound rotor type is it requires maintenance because of the brushes and the slip rings, but its advantage is just having access to the rotor winding. Okay, guys, so just being able to access the rotor winding actually is considered here an advantage. Okay, guys, for the squirrel cage, yeah, we are losing this advantage. We cannot access the rotor winding. Okay, so you cannot access the rotor winding, and this actually is a disadvantage. But on the other hand, and keep that in mind because that's very important, and that's why this kind of motor is a very, very popular, is as an advantage for the squirrel cage, the rotor is very solid and requires almost no maintenance. Okay, you just have a very, very solid rotor. If I need to grab you those realistic photo for the squirrel cage rotor, I think I have one somewhere here. Yeah, the same one we used before. Yeah, okay, so I'm gonna give you this, just the rotor shape of it. Okay, so that's your rotor. Okay, yeah, so like you've seen here, that's an actual rotor of a squirrel cage machine. Okay, you can barely see actually here the bars. So those lines here, your bar, and this is the, so those are the bars, and this is the end ring. Actually, you have another one down here also, that is another end ring. But like you've seen here, it's just almost a piece of iron, the whole rotor. It's very, very solid, okay, and does not have any connection to the outside world. Yeah, it's a disadvantage because you cannot control the rotor circuit, okay, but you have a huge advantage that is almost a maintenance-free machine. It's almost like no maintenance required for this rotor. It's just very solid, okay, and does not have any terminals and does not have anything to just worry about. So it will handle very harsh operating condition without being just so much concerned about it. And like we said before, as an engineers, all the time we like to have stuff that requires no maintenance. We can put a lot of effort in the planning stages, in the manufacturing stages, in the design stages, but once we jump into the operation, we have a system running. We need this system to be just having less headache as much as we can. We like to leave the system and just forget about it. And the squirrel cage give you this big advantage. And that's why that's a very, very, very commonly used kind of a motors. So the squirrel cage 3-phase induction motors is actually what we said, or what we meant by the workhorse of industry, okay? So the wound rotor type does not as much popular as the squirrel cage. So the squirrel cage is actually the most widely used one, okay? So it's a huge advantage to keep in mind here. It requires almost no maintenance, and that's actually a very huge advantage for the squirrel cage, okay? But as a theory of operation, how they work, they are just identical, okay? They will do the same stuff for you. Both of them are just 3-phase winding put in the slots and just short-circuited, okay? With difference of how we short-circuit both of them, how you can handle both of them, but they are just exactly the same. They're sets, both of them, as just sets of 3-phase winding connected or just short-circuited, okay? And that's what you need from your router. So both of them, actually, we can model them the same way. We can deal with them in terms of calculations and modeling and all that stuff at the same way, but in reality, or how they acting, they are just slightly different in terms of construction. So in construction wise they are different, but modeling wise, okay, how you mathematically model them, that does not have actually differences that can we consider, okay? Sounds good. So those are your two different types of rotor, okay? So let me now jump to talk to you how the rotor field now happens. So just to remind you what we were talking about, we talked about that we need to understand how is actually the torque is produced in this kind of a motor, because that's the theory of operation, how the machine works and how the torque is produced, okay? So like we said, to have a torque, we need to have two components of fluxes. One comes from the stator and one comes from the rotor, yes? The flux of the stator comes from the 3-phase voltage applied to the stator that will push electric current into the winding, and that creates magnetic flux in the stator. Okay, so let's now talk about where the other component of flux comes, which is the rotor flux. Now we understand the construction of the rotor, okay? But like we said, the rotor winding are short-circuited. Whatever you're talking about, a slip ring rotor or a squirrel cage rotor, they are short-circuited. They are not connected to an external voltage source to apply electric current to them and create magnetic field, just like the stator. So where the magnetic field of the rotor comes from, like I said, it comes by induction. How this happens, we will now talk about it, and we're trying to understand the theory of operation. So now I'm talking about the very important part, which is theory of operation. I'm gonna take it as steps and follow me, because that's very important. So number one, the stator 3-phase winding are connected to 3-phase voltage source, okay? Both of them are balanced. We don't need to say that all the time. So you have three-phase voltage applied to the three-phase stator winding, and this creates rotating magnetic field, okay, like we said multiple times now. Yeah, this rotating magnetic field rotates at the synchronous speed ns 120 f over p. Okay, now let's look at the rotor. Okay, now the rotor winding will be exposed to the stator field, okay, which is rotating, and that means the rotor winding will be cut by a time varying magnetic field of the stator. Okay, so you have a magnetic field coming from the stator, and this magnetic field will cut the rotor winding. Okay, and this will be seen by the rotor winding as a time varying. Okay, why? Because at starting, what you're talking about at the starting point now is the rotor winding are stationary. It does not rotate it yet, okay, so are stationary, and the stator field rotates at the synchronous speed. Okay, so you're having now a stationary coil on the rotor and a rotating magnetic field of the stator. So this stationary coil on the rotor will be seeing a change in the magnetic field. Sometimes just a north pole, and then comes a south pole, and all that stuff. Just imagine it like that. You have here a north south pole on the stator, and those are just running around like that. And now look at the rotor winding here. So any winding on the rotor like that, that's winding on the rotor, will be sometimes seen a south pole, and after it rotates it will come another north pole. So this winding and the rotor will be seeing a south pole, then a north pole, and even though south pole and north pole is just are coming from AC supplies. Okay, so just running around like that. So those rotor winding will be seeing a time varying magnetic field. Okay, and that's what all you need to have a generation axis. Okay, it just what it needs to have like this. So the time varying magnetic field of stator that cuts the rotor winding will induce electric voltage on them. Now your rotor winding will have an induced voltage because they are just subjected to a time varying magnetic field. Okay, if you remember the Faraday's law we just dealt with before, E equals BLV. B is the magnetic flux, L is the length of the wire you're talking about, and V is the speed. Okay, now you have a speed because you have a rotating magnetic field. Actually, it's just another form of the same thing you dealt with in your physics courses before, which is minus N d phi by dt. E is also the induced EMF. N is the number of turns you have in your coil, and here is the whole thing, d phi by dt, a time variation by the magnetic field, which is caused actually by this V, which is the speed. Because the magnetic field is running at a certain speed, it will have a time variation like this, and this will have you an induced voltage in the rotor winding. Okay, so your rotor winding will be having an induced voltage on them. Okay guys, now what? Here comes the magic. Okay, and that's why, because the rotor winding are shorted, the voltage induced on them is applied to a closed path because it's short-circuited, so current moves in the winding, creating flux. Okay, so like we said, we have magnetic field coming from the stator. The rotor winding sees as time varying because it rotates all the time, and this will induce EMF voltage on the rotor winding. But that's not enough. If the rotor winding are opened, that will not make anything. But because you have a short-circuited rotor winding, we have just short-circuited the rotor winding, those are now a closed path. So if you have a voltage induced on this closed path, it will pass current through the winding. It's just an Ohm's law now. You have a voltage applied to a closed path, so an electric current will start moving through the winding. And a current moved through a winding will create its own magnetic field. And that is now your rotor flux, which is the second component of flux. Remember, the torque requires a rotor flux and a stator flux, BR and BS. Okay, like we said, BS comes from the three-phase voltage source applied to the stator, and the rotor flux comes from current induced by the stator flux cutting the rotor winding. Okay, it comes by induction, and that's why this machine is called an induction machine. Okay, guys? So now we have our second component of flux. So now the torque will be just created. Okay, so here's the whole point. This, or current induced in rotor winding, is also balanced three-phase current moving in balanced three-phase winding. Okay, because like we said, the rotor is just like the stator. It's also a three-phase winding, and the voltage that will be induced in it will be three-phase voltages, just like the stator, and it will just pass a three-phase current, also balanced like the ones moving in the stator. Okay, so the rotor current, or no, that means the rotor flux, sorry, will be also a rotating magnetic field. Okay, so you'll have and the rotor just like the stator. So your stator will have its own poles, like a north pole here and a south pole here, something like that, and this guy are just, those two poles are rotating around it with the synchronous speed. Okay, the rotor will be just having the same thing. So here you will have a south pole, and now you have a north pole. Okay, this north pole and south pole, north pole of the stator will be coupled to the south pole of the rotor, and the north pole of the rotor will coupled with the south pole of the stator, and both of them will be rotating at the same speed. Okay, the stator field and the rotor field are coupled together, rotating at the same speed, which is the synchronous speed, and dragging the rotor body to rotate behind them. Okay, so you have a rotating magnetic field of the stator coming by three-phase excitation coming from the three-phase source applied to the three-phase winding, and you will have also a rotating magnetic field in the rotor comes by induction from the stator. Like we said, you have a short-circuited three-phase winding in the rotor subjected to a time-varying flux coming from the stator. So a voltage will be induced in the rotor that will be also three-phase like the stator one, because it's coming from three-phase stator winding, and this will be applied to a three-phase rotor winding. So you'll be having the same condition in the stator, a three-phase voltage applied to a three-phase winding, and this will create also a rotating magnetic field. The poles of the stator and the poles of the rotor will be magnetically coupled. That means they will be attracting each other. The north pole of the stator will attract the south pole in the rotor. They will be coupled together and rotating at the same synchronous speed, 120 F/P. Okay, and while this happens, it will drag the rotor body itself to rotate behind them, and this how the torque is created in this machine and how the rotor actually rotates. Okay, guys, so you're just talking about that the rotor of this machine is now starts rotating. So we saying that the rotor body starts to rotate behind them, and that's how the torque is produced, and that's how the machine is just working here. Okay, guys, but here's a very, very big hint, and that's why I'm saying the rotor body is just rotating behind them. Okay, that the rotor body is rotating at a speed less than the speed of magnetic field of the stator and rotor, which is the synchronous speed. Okay, so the Nm, the mechanical speed, less than the synchronous speed. Nm is the rotor mechanical speed. Okay, Ns is the synchronous speed, which is the speed of the stator and rotor magnetic field. Okay, guys, why this has to be, why the rotor body itself has to be at a less speed than the speed of the magnetic field? Why? Otherwise, the rotor winding will be at the same speed of stator field, and that means it will see the flux fixed, so there will be no time variation in flux cutting the rotor winding, and that means the induced voltage, the EMF induced, or the E induced in rotor winding now will equal 0, and there is no current IR, no current in the rotor winding, and that means no magnetic flux in the rotor, and this will come at no torque at all, and the machine stops rotating. Okay, do you understand what I'm saying, guys? It is just the whole point. Remember, like we said, why this all happens, this induction stuff happens, because the rotor winding are seeing a time variation in the magnetic field. It's how the Faraday's law of generation works. Okay, so the rotor winding are not connected to any external source to have its own electricity, so it gets this by induction from the stator, and that means the rotor winding all the time has to be seeing a time varying magnetic field. Okay, so we're saying that the magnetic field of the stator is rotating at the synchronous speed. Imagine if the rotor body, which is the same like the rotor winding, the coils on the rotor are rotating at the same speed, which is the synchronous speed, the same speed as the poles of the stator. They will see it at fixed. Okay, imagine that here the north pole, or just look at here, so that is the north pole of the stator and that is the south pole of the stator, and this guy is just rotating in this direction at the synchronous speed. Look at now any conductor on the rotor. Okay, let me look at this conductor of the rotor. Okay, if this conductor just rotating at the same direction like this with the same speed, okay, so those will be just rotating together all the time. So this guy will be seeing a north pole all the time because they're just rotating together at the same speed. So this conductor will be seeing no variation in the magnetic field. And no variation in the magnetic field means there is no induced voltage, because the induced voltage comes from the variation of the magnetic field, not the magnetic field itself. Okay? Remember, like I said here, this guy comes from here. E equals minus n d phi by dt. And it's also coming from this speed term. Okay? You do not have this term because the rotor conductors will be just having the same speed with the poles of the stator, so it will not be seeing any variation in the magnetic field whatsoever. So this d phi by dt will equal 0, and that means this induced voltage in the rotor winding will be 0, and without voltage induced in the rotor winding there will be no current moving in them, and no current means no flux, and this means you are losing your second component of flux, and the torque will be 0 and the motor will stop rotating. Okay, so that's how we understand this, guys. So keep that in mind. That is very, very important to have it here. So the rotor body, which is the rotor core, I'm saying, and winding rotates at Nm, while rotor flux rotates at ns synchronous speed, and Nm is less than ns. Okay, guys, so the rotor body and the rotor winding, they are just dragged behind the field, and that's how we understand this. So the field, so the speed of the field is just superior, is higher, it's the synchronous speed, it's higher than the actual rotor speed, which is Nm, which is slightly just behind the synchronous speed. And you have to keep, or just the machine acts like that. It has to keep this difference between the synchronous speed, which is the speed of the magnetic field, and the rotor actual speed, because if there is no difference in speed, there is no variation in the magnetic field seen by the rotor, and there is no induction, which is the whole theory of operation of the machine. Okay, guys? Okay. Take some time to digest this. Study it more than once, because I know it needs some time to understand what's happening in each time. It's a little bit more complicated than the other types of machines, which is very straightforward. You have a source for the stator, another source for the rotor, so you understand where each field coming from. But here it's a little bit just tricky to understand what's happening. So the field of the rotor comes by induction from the stator, and that's why we call it an induction machine. But that's why it's a very brilliant idea, because like that you don't need to attach any other source to the rotor, and the rotor will just can run freely without connected to anything other, and this will just save you from a lot of headache by using the brushes and slip rings to push external voltage to the rotor winding. Okay, sounds good. Okay, thanks so much guys for joining me today. Take time to just digest that, and I'll be seeing you next time.